Hey guys, welcome back. I was at the scrapyard the other day and picked up some goodies. So I got, you can't see shit here. Got myself 2 angle grinders, one from Flex and one Bosch Blue. Paid $7 for each. Additionally to that, I picked up this VFD here, and now I've got this monstrosity set up. We're going to tear it down, have a look how it's built and how it works and how it compares to the other one that we tore down, this Chinese piece of crap. So let's jump into it. Here's what we got. This is a Telemecanique VFD produced in France. There's the part number if you want to look it up. It's actually I don't know if it's just the control system or if the whole thing is called the Altivar 11. Basically, it's a 3 or 2 horsepower output, single phase input, 3-phase outputs. Yeah, works on 50 to 60 hertz and can put out between 0.5 and 200 hertz. Just having a look at the case here, so it's been a little bit banged up. I found it actually at the bottom of the garbage bin at the scrap place there. I decided to pick it up because basically they just gave it to me. The idea is to try to figure out what's wrong with it and fix it. Basically, it's the standard little control panel here. Under here, you have your little I/O. You can connect various circuitry there. First thing that we can notice as compared to the other one that we had a look at, so the casement here is, I don't know if you can see, there you go, polycarbonate. So nice plastic. This little case is also, I just saw it somewhere, also made from polycarbonate there. So right off the hop, it's way nicer than the Chinese one we had a look at. By the way, these things, they run at 300 some odd volts on the DC bus. So the DC bus is right here. If you don't know what you're doing, don't fuck with this. It's going to kill you. The power comes in actually on this board right here, but we'll get to that afterwards. So after it goes through this board, which is the EMC filtering board, it goes to this main board right here. And here's where the power comes in, plus minus. This is obviously also a 3-phase VFD. So here's a empty place for a 3rd phase. At the moment, we just have the L1 and the L2 here. This directly goes into a module, which is under the PCB here. So if we flip it up like that, you see the module right here. And this is a EUPEC, I'm not sure how that's pronounced, but it's basically an IGBT module together with a full wave bridge rectifier. So inside there are 6 IGBTs, 6 diodes. So I'm not sure why they have 6 diodes rather than just 4, but what happens is the power comes in here. It gets rectified by the full wave bridge rectifier, which is down in that module. And then it goes to the DC bus. So basically once it's rectified, it goes directly to these huge caps here. This is all charged. There's actually 3 of them. I'm not sure what the capacity is, but there's 3 of those guys in there. And there's actually even place for a 4th. Maybe they use that when it's in 3-phase configuration. And after we have the DC bus, you can see it's that cold in here. After the DC bus, basically we split off into this portion of the circuit here, which is a flyback converter. So there's a little transformer which generates the various voltages which we need. I think it makes plus 15, minus 15, plus 12, minus 12, something like that. This little IC that you don't really see, so that guy right there is actually the the flyback converter regulation circuit. So it's doing the kind of closed loop monitoring of the voltages and switching this power MOSFET right here in order to generate the voltages here at the transformer as they are required. So it's got a little shunt resistor right there. I don't know how much it is, 1R5, and it's measuring, this is basically in series with the drain source of this MOSFET. There's a little measurement feedback in this IC. It's measuring the voltage drop across this resistor and setting the switching behavior on the gates of this MOSFET such that at this transformer all of the voltages are set how we need them. This guy here is a relay. So what the relay does is if you were to plug this into 220 with these caps directly shorting line and neutral, what would happen is you get a enormous current spike which will pop your breaker. So the way that they deal with that is they have this relay, and I'm not sure that you can, yeah, you can see them. Whether they're in focus is a different question, but you can see them. So in there, there's two boards, basically power resistors. So it's 50 ohms per board. It looks like they're in parallel, so there's probably going to be 25 ohms there. And they, on startup, switch this relay open and disconnect the line and neutral from the capacitors directly, but they rather pass it through this relay and through those resistors to slowly charge up the capacitors and prevent the huge current spike. When they're charged up, this relay opens and then it works normally. So then moving on this direction, here we have the microcontroller. I'm not sure what the controller is. I don't really want to pull this off and yeah, destroy the conformal coding here, which is actually another big difference to the Chinese VFD we looked at. So the micro, there's one here, there's also one in this board, both conformally coded to protect them from all kinds of dirt and dust and other various crap, which is nice. The entire board's not conformally coded, but I've actually understood now why that is. And it doesn't say here on the side, but it's it fits to the IP class that this is rated. So the dust and water and whatever ingress specification, this IP specification, it doesn't have a very high IP, so it's maybe protected like against basic dust ingress, and that's why they don't need to conformally coat the entire board. From the micro, there's here a little 5-volt voltage regulator, 7805 from ST. So this pulls one of the voltages from the transformer here and gives you your 5 volts, which powers the micro, and presumably the rest of these ICs as well. Here we have an EPROM. So I guess when you set the settings, how you want them and save them, they get saved here in the EPROM. Then this guy, I actually didn't really understand what it's doing. It's some kind of binary counter. So if somebody has some ideas, let me know what that could be doing. Here we have a couple of little connectors that go out to the control board. All right, I was totally on a roll there, then I got interrupted. Yeah, connectors here. Okay, so these connectors go to the front panel, and I presume that there's some kind of serial communication interface there, because on the front panel board, we also have right there a micro. And so I guess they just talk to each other over these connections here. Another really significant difference to the Chinese VFD, and what's actually really scary about the other one, is the entire heatsink of it was floating, and they had basically 4 millimeters between the contacts of the DC bus and the heatsink. So you have a floating piece of metal that's not grounded to anything, and 400 volts 3 millimeters away from it, which is all kinds of not cool. This one, if we have a look at it, there's 2 grounding points, one right here, which is connected to this screw, which is connected to the ground of the PCB, which is connected to the heatsink, and everything is happy and connected together. They even have one here, also connected to this screw, and the flyback converter here even has a filter cap which goes back to ground, which is all kinds of cool. Likewise, in this corner, we have also 2 capacitors connected to this ground. So lots of thoughts went into this layout, lots of thought went into safety, which is why you pay money for a good VFD. Another thing which I wanted to mention, which I found quite interesting, somebody's actually taken care for this layout. So there was some thought put into this. If you notice, this is going to be like our power ground plane right here. So this is the DC bus minus. The shunts come on here. So this is basically the source of the low side IGBT from the IGBT module. The minus of the DC bus, and it's where the current is measured and everything else. This side here is going to be our kind of analog ground plane, or logic ground plane, however you want to call it. And here in the middle, if you notice these three little connections, there, there, and there, that's a start point between the two grounds. So somebody's actually thought about the current flows and the EMC behavior and how this board is laid out. Maybe that's not even for EMC, maybe that's just purely from a signal integrity perspective. They keep the, let's say, low noise items on the analog ground or the logic ground and the high noise items here. And because they need a coupling, they control the coupling, which is right here. So that's actually a really good sign that somebody took care for and put some thought into this layout, which again reflects the quality of the entire device. Moving on in the circuit. So here, this section here, so here there's some kind of population option, which isn't there. Maybe that's for some other options that this guy doesn't have. This guy right here is a amplifier IC. So inside there's 3 amps, which are reading the voltage drops across the 3 shunts here, which measure the currents of the 3 phases. So from the IGBT module, so you're going to have a high side IGBT. IGBT is an insulated gate bipolar transistor, by the way. It's kind of like a MOSFET, but a bit more fancy. Right, so here we have DC bus. This is the high side. This is the low side. Here in the middle, we have the phase connection. So this is actually to one phase of your 3-phase motor, right? So here, for example, you have U, V, W on your motor. And this is one phase. Now, this little shunt here, this is sitting exactly right here. Okay, this is then the ground. And this IC here has 3 differential amplifiers in it. So basically you have one connection here and one here across your shunt. This goes over to a differential amplifier. Okay. There's going to be some other filtering and conditioning. You can't see shit, can you? Sorry about that. There we go. Here there's going to be some other filtering and conditioning components, so most likely there will be a series resistor on both of these. There will probably be a X capacitor. There's probably some Y capacitors. Something like that will be there. From this amplifier, what I would expect is, so here we have 20 milliohm. So here there's going to be relatively low voltages. Yeah, and this amplifier will amplify that to the full scale range of the ADC of the microcontroller, right? So this is a 5-volt micro. I presume also the ADCs are 5 volts with maybe 4096 bits, and then you would get into the ADC of the micro here, which is going to take this voltage, which is here still analog, right? So here we're going to have an analog voltage from 0 to 5 volts roundabout, and this micro ADC, what it does is basically take that voltage with it's probably a sample and hold ADC, and it takes that and converts it into digits. So from 0 to 4096, if it's a, correct me if I'm wrong, 12-bit ADC should be 4096. And basically you get a number then inside of the micro, which you can use in the software, ranging from 0 to 4096, which represents the analog voltage of 0 to 5. So 5 volts here would be 4096 digits inside the micro, and 0 would be 0. On the Chinese VFD, we saw they were measuring currents in 2 phases, and they were doing it with a resistor. So resistors are not the best for measuring. A little break here. The shunts are going to be significantly more precise, and if you have a more precise current measurement, you're going to be able to set your phase currents better and therefore control your motor much more cleanly and nicely. Also, you can get away with measuring the currents in just 2 phases because the motor that you're connecting this business to has a start point, and we know that at any node, the sum of the currents equals 0. So if you have 2 of the 3 currents, you can calculate for the third. However, they measure it in 3 phases. I'm not exactly sure why. It seems excessive. Maybe if somebody knows, drop a comment below. These guys here, which are the gate drivers, the IGBT drivers. So each chip is responsible for the high side and low side IGBT of each phase. And actually, it's a little bit curious how they've done it. So this guy here is actually doing phase W here. This guy is doing phase V, and this guy is dealing with phase U. Then we have here additionally 2 terminals, and those are DC bus outputs for which you can use them to put an electric brake on your system, whatever you're powering. And this guy here, this is a little bit curious. They basically route this, I think it's the negative of the, no, the positive of the DC bus. They route it from here. So this is the output, no, this is the source of the DC bus right here. And they route it over here. I guess they didn't have enough place on the PCB, or the currents was too high, or whatever. All right, so that's kind of it to the circuits. Like I said, really well built. Everything looks quite nice. There's a fan there, big heatsink on the back. The IGBTs are thermally glued onto the heatsink. That all looks really nice. And okay, so that's so much to this part of the circuits. All right, let's quickly go over the other couple parts of the circuits, and then we can dig into what's wrong with this thing. So here's the casement where we put line, neutral, and ground. There's the outputs on this side. This is this DC for the brake. And here inside is another PCB, which we can take a look at. But I need a screwdriver. What is that? Torx. Okay, grab some screwdrivers and let's pull this guy out. And again, if we have a look at the other, by the way, I'll leave a link to the video of the Chinese VFD and just have a look at what's going on there and compare it to what's going on here. So in the Chinese VFD, we had basically a capacitor and a choke to deal with the EMC. And here we have a completely different level, right? So I guess the Chinese one didn't actually do any compliance testing. It's probably completely illegal to plug into the European nets. Here the power comes in. There's even, you see there's screen protection PCB, really interesting, soldered in there. So first we hit a capacitor, X capacitor, so between line and neutral. Then we have a huge common mode choke, which basically, so any noise generated by the PCB will try to go back out onto the grid, and this thing will converts the currents which are flowing in the same direction, right? So if you have noise going on line and neutral out, they're going to create a magnetic flux, which is going to be additive in the core. And this ferrite core right here, the higher the magnetic flux through it, the higher the impedance. So the more common mode current you have trying to go out, the higher impedance you have here in the common mode choke. And if you have currents going opposite directions, the magnetic flux generated from those currents essentially cancel inside the core, and they can just flow how they want. So then we have a couple more caps here. Another cap. We even have on the connectors which go down to the PCB another ferrite core. And then, like I said, the two ground connections, which are also a nice addition relative to the other one, to the Chinese one. This is maybe not so cool, so that's kind of a big component to just hang off of two little soldered leads. You would like to maybe see some glue, which I find a bit odd because the common mode choke here, if you look there inside, it is glued down. But this guy here is just kind of sitting there. That's not great. But overall, not bad. So the PCB quality is really nice. Nothing to complain about here. So the final component, we have this little front display panel. And this is how it looks inside. There's a microcontroller. There's a little voltage regulator here. Some optocouplers. And another voltage regulator here. So this is a 7805, I guess, to power the micro. This is a 317, so that's a settable voltage regulator. They're both linear regulators. So they take this pin right here is the power for this guy, and they take the power that comes in and regulate it to whatever they need. Here you have your various outputs. Yeah, they're listed here, what they are, but it's not super important for us at the moment. Okay, good. So now that we know kind of how this thing works and what it's doing, we can start troubleshooting. So the first thing I did, I plugged this in without disassembling anything, and basically nothing happened. Okay, so my first thought was maybe it's a fuse or something like that. I opened it up. There's actually no fuse inside this thing at all, and it's completely dead. But it does make a whine, which is noteworthy. So my first thinking was then to isolate the problem first on this board. So I did a continuity check. You can do it actually together here really fast. I can just show you. Set your meter in continuity mode. Make sure it beeps. Take your various inputs. So this is ground. Ground has continuity to both grounds. That's all fine. Then one of these guys is going to be the line and one's going to be neutral. So this is in, it gets filtered. Here it goes out to the next board. Here we have continuity. Here we might have momentary continuity from the caps, but it shouldn't be always there. Then here is the other pin that has continuity there, maybe momentary here. Nope. And so we know this board is not the issue. Its job is to filter the noise, and its job is to get the voltage from the wall here to the board here. So basically, this is not where our problem is. So we can basically throw this guy out, not throw it out, but set it aside. We know this is not where the issue is. So next step is this guy right here. Now I did all of this powered off camera. I don't want to do this powered on camera because if I miss somewhere while I'm looking at the screen and electrocute myself to death, that's going to be not so cool. So I'll just kind of go through my thinking process here. Right, so the first step was then to open it up, to go through the circuit to understand it basically. So if we have nothing happening when we plug it in, that tells me either fuse blown, something's not getting power, something burned somewhere in this direction. So here's where these pins come in from the EMC filter. And then the next step is basically the rectification from the IGBT module. So what I did then was test the DC bus. Do we actually have voltage there? And we did. We had 300 some odd, whatever it is, volts DC. And the next step from that, so we know, okay, the rectifier is working. The DC bus is there. That means all the caps are more or less working. Nothing's shorted. Everything's okay there. Also, really important indication, it didn't blow the fuse in my house when I plugged it in, so nothing is hard shorted inside, right? So we know something's got to be open, most likely. Okay, so the DC bus, like I said, has power. And the next thing that I noticed when I plugged it in, it makes a kind of high-pitched whine. And when we analyze the whole circuits, the only place where there are any switching components except on the actual IGBTs is the flyback converter. So here we have a linear regulator. On the other board, there's all linear regulators. There's no switching converter anywhere except right here. And the high-pitched whine in this device could be generated from, I would say, one of two things. Either this flyback converter or the IGBT switching, because those also have a switching frequency, which is going to be like in the kilohertz range, which is in the audible range. So you'll hear it. Next step was then to measure output voltage of this circuit right here. And I did that by taking this circuit into consideration. And I've identified here that this pin right here, the 2-pin connector, is actually the power for this board. And these have to be the communication. And the way I figured that out is the power connector is here right next to the voltage regulator. And also the connectors here, and these two are next to the micro, so that tells me those are more the communication ports. And this guy here, the 2-pin, is directly next to the flyback converter, so that tells me this has to be the power. So I measured the power here. We had around 8 volts. Now the input of this guy, this is a 7805. It should work fine on 8 volts. However, this screen, nothing here was lighting up. This was completely dead. So what I was thinking is maybe this board is actually okay, but this board is dead. So then what I did was plug this board into power. Actually, that we can do because it's not high voltage and it won't kill me. Okay, I've got the power supply set to 11 volts. Basically, the way you can determine what voltage to set it to. So we know this component is a 7805. We know from the data sheet that the input voltage is a certain range, and yeah, for a little bit safety factor, turn it down. But we also know that the flyback converter makes voltages of 12 and 15, so it's got to be one of those two. So I set it to 11 just to be safe. And then we can go ahead and put the minus on the minus and the plus on the plus. Okay, now it's pulling 30 milliamps, and you actually can't see that. Hold on, let me try that. Camera doesn't see that because I got a lot of light on here, but basically this screen lights up and it actually does stuff. So I think maybe you could see it, maybe not, but this lights up and it goes through some kind of self-check sequence, right? So that tells me this part of the circuit seems to be working, right? So we can even, I don't know if I can get this to stay. Yeah, it seems to have stayed on. Put the meter there where you can see it, set it to voltage, and then just try to measure some stuff. So you can see 10 volts, that should be the inputs, and there's the output. So the 7805 seems to be working fine. That's all happy. Then we can measure this IC. This is outputting, I don't know what that guy's doing. But basically this booted up, this did something, it did some self-check. So now on the screen, I can barely see it myself because of how much lights. 1HF. So this went through some kind of process, this checked something and it switched on. So that tells me that this part of the circuit is, or seems to be at least, working properly. Leads me back to this guy. If we open up the data sheet of the flyback converter, and have a look at this schematic. Then you can figure out which components are where. Probing around in this with 400 volts DC here and 220 line voltage is kind of scary with power on. So basically what I decided was that since this connector here, I measured 8 volts there when this thing was powered, and that little control circuit was not powering on with 8 volts, even though the 7805 should provide 5 volts from an 8 volt supply. That tells me that when this gets under load, it probably doesn't stay at 8 volts. It probably drops down and kind of dies. So what could be the issue? The MOSFET could be burned. The transformer could be dead. These resistors could be dead. The IC itself could be dead. Any of these little chicken food components could have failed open or short. I didn't find any data sheet from this transformer, but I've measured a couple of the coils which are inside, and it seems like this is not the issue. However, probably can't see that on the camera, but on these two resistors and here on the transformer, there's a little bit of like black soot. And I don't know if that's just from where this thing lived its whole life, because this is the top side, or if something exploded here. So that was my thinking first. I desoldered this leg of both of these power resistors and measured them, because you can't measure a resistor in circuits. If there's anything in series with it that's in parallel with it that's of a lesser resistance, you won't measure your resistor. You'll measure some combination of whatever else is in the circuit and this guy. So to measure them really properly, remove one leg and measure across. These both checked out fine. So I figured it's not there. I checked then the whole path from this resistor through the transformer to the MOSFET. That's fine. I checked the MOSFET ground. That's fine. I checked the gates of the MOSFET. It's connected through a resistor to the IC. That's still all connected. That's fine. Shunt resistor's fine. Then I found one thing. So on this IC, there's a self-generated 5-volt reference voltage on, I think, this pin here on the corner. And that reference voltage was at 1 volt. So that was the first indication that something here is not right. So what I've done, and we're going to see the results of this later, is I ordered the MOSFET new, and I ordered this IC new. Basically, you can just Google the part numbers, go on eBay and find them. They were like $5 for both parts. This guy is here, the IC is not here yet, so I'm going to continue this video once they arrive, but basically that was how I went from having this, what seems like quite complicated device, which doesn't work, to narrowing down the problem to one of two components or a combination of both components. Now, I don't know if that's going to fix this circuit, but we're going to start there and eliminate those two first. If that's not it, then we're going to start digging further, and my next target is probably this transformer, because I don't really like this black stuff that's here in this region, but I don't see anything else that's dead. And yeah, so we're going to wait for these guys to come in the mail, and then I'm going to continue this. I don't know if I'm going to stop here or if we're going to make a second video or how this is going to go, but in case I stop here, thanks a lot for watching, and see ya in the next video.